the origins of the universe, Earth, and life. The term evolution extends beyond its common association with biological evolution, the gradual development of living organisms over time. It also describes the dynamic changes and developmental processes of planets, stars, galaxies, and the universe itself. Each of these entities undergoes transformation through different mechanisms, but shares the fundamental concept of evolution as a progressive alteration over time. This broader perspective of evolution allows us to explore the cosmic and geological processes that have shaped the universe, our solar system, and eventually life on Earth. In the late 1920s, American astronomer Edwin Hubble made groundbreaking observations that significantly altered our understanding of the cosmos. By examining the light emitted from distant stars and galaxies, Hubble observed a redshift phenomenon, a displacement of spectral lines towards longer wavelengths. This redshift indicated that these celestial bodies were moving away from Earth. More intriguingly, Hubble found that the velocity at which these galaxies receded increased in proportion to their distance from Earth. This relationship, now known as Hubble's law, suggested a uniformly expanding universe. Hubble's discovery provided compelling evidence against the static universe model, which posited that the universe had always existed in a stable, unchanging state. Instead, the expanding universe model implied that the cosmos was once much smaller and denser. This notion led to the revolutionary idea that the universe originated from a singular, highly condensed state, a concept that would evolve into the Big Bang theory. The Big Bang theory posits that approximately 13.8 billion years ago, the universe began as a singular, infinitely hot and dense point. This initial state contained all the matter and energy that would eventually form galaxies, stars, planets, and life. A colossal explosion, or bang, caused this primordial mass to expand rapidly, setting off the ongoing expansion of the universe. As the universe expanded, it cooled, allowing particles to combine and form simple atoms, primarily hydrogen and helium. This cooling and expansion phase allowed matter to clump together under the influence of gravity, leading to the formation of galaxies, stars, and eventually planets. The Big Bang theory also predicted the existence of cosmic microwave background radiation, a residual thermal radiation permeating the universe, which provides a snapshot of the universe shortly after the Big Bang. In 1965, Arno Penzias and Robert Wilson discovered this cosmic microwave background radiation, providing empirical support for the Big Bang theory. Subsequent missions, such as the COBE satellite launched in 1991, confirmed that this background radiation exhibited the precise characteristics predicted by the Big Bang model. The discovery of this radiation was crucial in establishing the Big Bang as the dominant cosmological theory explaining the origin and evolution of the universe. Formation of galaxies and stars. As the universe continued to expand, matter began to coalesce into large clouds due to gravitational attraction. These clouds, composed primarily of hydrogen and helium, condensed and started to rotate, forming the precursors of galaxies. Within these nascent galaxies, regions of higher density began to collapse further, leading to the formation of distinct clouds of gas and dust. In certain regions where the mass and conditions were suitable, gravitational forces caused these clouds to collapse further, initiating nuclear fusion reactions. These reactions marked the birth of stars. Stars form in various sizes and masses, and their evolutionary paths depend on their initial mass. In massive stars, fusion proceeds rapidly, leading to a shorter lifespan and eventual supernova explosions. In smaller stars, like our Sun, the fusion process is slower, resulting in a longer, more stable life cycle. Formation of the solar system. Our solar system formed about 4.6 billion years ago from a rotating disk of gas and dust surrounding a newly formed star, the Sun. This disk, known as the protoplanetary disk, contained various elements and compounds that would eventually form planets, moons, asteroids, and comets. Within this disk, particles collided and stuck together, forming planetesimals, small, solid objects that ranged in size from a few kilometers to hundreds of kilometers. Over time, these planetesimals collided and merged, forming larger bodies through a process known as accretion. The inner region of the disk, where temperatures were higher, led to the formation of rocky planets, including Earth. In contrast, the outer regions, where it was cooler, allowed for the formation of gaseous and icy planets. The formation of the Moon is believed to result from a massive collision between Earth and a Mars-sized body early in the solar system's history. This impact ejected a significant amount of debris into orbit around Earth, which eventually coalesced to form the Moon. This event significantly influenced Earth's evolution, contributing to its axial tilt and stabilizing its climate. Modern scientific techniques allow us to estimate the ages of the universe, our galaxy, the solar system, and Earth. The age of the universe can be derived from Hubble's law, which relates the velocities of galaxies to their distances from Earth. By measuring the rate of expansion, known as the Hubble constant, astronomers estimate the universe's age to be approximately 13.8 billion years. The Milky Way galaxy's age is estimated using two primary methods: the study of star clusters and the analysis of long-lived radioactive elements. Globular clusters, which are spherical collections of stars orbiting the galaxy's core, provide valuable insights. These clusters contain some of the oldest stars, whose ages range from 11 billion to 16 billion years. Their composition, primarily hydrogen and helium with minimal heavier elements, indicates they formed early in the galaxy's history, before the enrichment of the interstellar medium by successive generations of stars. Another method involves measuring the abundances of radioactive elements, such as uranium and thorium, in the solar system. By comparing their current abundances with their decay rates, scientists estimate that the Milky Way galaxy is between 9 billion and 16 billion years old. These estimates align with those derived from the study of star clusters, providing a consistent timeline for the galaxy's formation and evolution. Radioactive decay also provides a means to estimate the ages of the solar system and Earth. Elements with known half-lives, such as uranium-238 and potassium-40, decay into stable isotopes at predictable rates. By measuring the ratios of parent-to-daughter isotopes in meteorites, which are remnants of the early solar system, scientists estimate that the solar system formed about 4.6 billion years ago. The oldest rocks on Earth, found in northwestern Canada and Western Australia, provide further evidence for Earth's age. These rocks, dating back nearly 4 billion years, contain zircon crystals that serve as robust timekeepers. By analyzing the isotopic composition of these crystals, geologists estimate that Earth's age is approximately 4.54 billion years. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.